Whenever we're performing any kind of statistical test, it's important to understand where it is easy to make mistakes. So I want to talk to you about some of the common errors that we have in regression. Extrapolation is one way in which we can make an error. And extrapolation is essentially looking past the data that we are given. So for instance, on my first scatter plot, I have the years since 1970, and then I have price based on what the dollar was worth in 2005. So in years since 1970, I can see that this first scatter plot goes to 1982. And from 1970 to 1982, my data appears to be fairly, linear, and that I could use the model to essentially predict what's going to happen in, say, the year 2000 or 2015, etc. So the problem with that is now if I look down here at years since 1970, this is now starting at 1980, and what's happening now is clearly we have a downward trend, and then we've got some issues over here. So if I would have not had this data and I just looked up here, I could mistakenly assume that this trend of increasing prices would continue and continue and continue, but based on the real data, we can see that that is not the case. So extrapolation is when you go past the furthest x value to predict past that. Another error that it's easy to make is to predict, so beware of your wording. So given the regression equation, calories hat equals 89.5 plus 2.5 times sugar, we may be tempted to say that adding a gram of sugar to your cereal adds an additional 2.5 calories, because that is our slope. But remember, we can't say that that's exactly the cause. We're saying, based on our model, so whatever model we had where we came up with this regression equation, for each additional gram of sugar, cereals tend to have about this many more calories. But in reality, a gram of sugar is 3.9 calories. So again, be very, very careful. We're not saying that it's caused by, we're saying this is the trend of data. Another error is when we have outliers. So looking at the outliers, I can see that I definitely have an outlier way up here. I have all of this data that looks great, and then an outlier. And we went through an example where we changed one of our data points and kind of showed what happened. But the first scatter plot has an equation that has an r squared value of 42.8%. But then if we actually take out the outlier and just make a regression equation based on all of the blue dots and not the red dot up here, now all of a sudden we have an r squared value of 82%, meaning 82% of the variation in Buchanan votes is accounted for by Nader votes. So obviously this is a much stronger model, and we're able to do that by taking out just that one data point. Leveraged or influential points. So a data point whose x value is far from the rest of the data is said to have high leverage. So here I've got this giant group or cluster of points, and then much, much, much further beyond that, I have a point up here. Notice that there is a great x distance involved in either of those examples. So those are both leverage points. Now, if the leverage point has the ability to pull the regression line strongly, it's said to be influential. So if I take this out of it, or take this out of it, if it changes my equation and it changes my r squared value, then it's said to be influential. So here is some of the data from before. So removing him from the analysis on the first scatter plot, we change r squared from 0.25 to 0.007, and that's huge, because 0.25 we can say, well, there seems to be a bit of a trend. 0.007, we would say that our model, our linear model, doesn't account for hardly any of the variation, so we shouldn't do linear regression. And on our second, our slope would go from 0.96 to negative 0.69. So obviously that made a huge difference, because here our slope would have been positive. Adding this point gave us a negative slope. So those are the leverage and influential points. Also, there are lurking variables, and we talked a little bit about this before, looking at life expectancy in doctors per person or TVs per person. It seems like there is a linear trend. So the increase in doctors per person increases life expectancy. The increase in TVs per person increases life expectancy. to an even greater degree. But again, we have lurking variables that could explain both the number of doctors per person and the number of TDs per person, which would probably be like socioeconomic level, standard of living, etc. So again, don't just assume because they're in a scatter plot together that one caused the other. Correlation does not imply causation.